Hi, everyone, and thanks for coming. My name is Jack. I'm here to talk about network isolation for 1,500 microservices. So, I'm talking about some work that I actually did at my last company, which is a large banking startup in the UK, and I'm just going to try and refer to them by the word bank from now on. So this company, they were cloud native from pretty much straight away, very early in the container wars, and they actually are now running a Kubernetes cluster that is about 4 years old, which I think is pretty mad. One continuous cluster that entire time, that even persisted across the CNI migration, which is pretty cool. And they're running 1,500 microservices that are almost all written in Go. So it's a very homogeneous platform, which made my life a lot easier. And I work primarily on security, but also a lot of core platform stuff. So it's self-hosted Kubernetes running on AWS. So by self-hosted, I mean that we are doing all of the management of it. We're using EC2, didn't use kubadmin, we didn't use any of the distributions, and we didn't use any managed services because essentially the platform predated a lot of that stuff. We also had a homegrown Envoy sidecar service mesh. In the early days, we were using Linkerd as a daemon set, but we ended up using Envoy as a daemon set, and then eventually went to Envoy containers in every single pod. And that was really awesome. And we ran our own control plane for that. And for networking, we basically were using Calico as a CNI, which worked fine, and we didn't do anything too magical with that. So you might have seen this picture before. I tweeted it a few months ago, and it got a lot of attention. What is this picture of? Well, this is actually what a bank looks like. The dots are services, basically microservices, and the lines are enforced networking rules between those services. So if you're interested in network isolation, this is a pretty good case study for how that can look like at scale. But I know it looks really, really chaotic. And that's partly just because this isn't really a good representation of anything meaningful. It's just a fun diagram that I like to show people, I guess. And with good tools, we create order in the chaos, right? So while this might look really complex, this isn't necessarily something that needs to be in anyone's brain. Unfortunately, it's not in my brain. And I'm not here to justify the whole concept of, are microservices good? Is this too many? What I will say is banks are complicated. And computers are fast. So by banks are complicated, I mean, you're not just looking at a database that describes the bank balance of everyone's account. You're also looking at an employee management system. You're also looking at a lending decisioning system. You're looking at a full support chat system that we built completely ourselves. And we weren't using a lot of third parties for stuff like that. You're seeing a diagram that has a lot of different stuff, and they're tightly interlinked, which is actually powerful. And by computers are fast, I mean, the latency is still fine, it's acceptable, especially for a banking product. People don't expect to get their balance in 5 milliseconds. We're not a high-frequency trading company, but instead, people expect us to build features really, really quickly. And feature velocity is really important, and an architecture like this actually allows us to deploy hundreds of times a day to never bump into other people's code. And I think that was really awesome. So I think this worked great for us. So yeah, the lines are network rules, and then enforced by network policies, just standard Kubernetes network policies, and obviously the dots are services. And managing these rules is actually really easy, surprisingly easy. And that's kind of what I'm here to talk about, is how do we design a system that manages rules like this so that it's safe, but also doesn't require a lot of toil. And if you start your cluster off with default deny rules and you tightly scope every single service, every single policy from day one, that's amazing. And over time, you'll have to refactor it into something that is more generic, but that would work great. But we actually started off with Flannel, and we didn't even have network policies. So you kind of have to come to a system that already looks like this, you just don't know it yet. And then you need to tightly specify the whole thing with network policies. And that was really hard. And keeping that up to date was also really hard. So how do we get going on this? Well, to start with, just to play around with the idea of network policies and what the power might be for us, we did some really basic things. So for new services, we did namespace isolation, essentially only allowing traffic from the same namespace. The reason we only did this for new services is that we didn't have a way of proving that it was safe for old services. So we just thought we'd do it from now on and then fix issues as they arise. But if an issue occurs on a new service, then it's usually caught before it affects customers. So the problem with this is that most of our compute was actually in the same namespace. We didn't have team namespace separation for various reasons. So it doesn't really give a lot of security value. This was kind of a test run. And this isn't just a security problem. It's also a monitoring problem. You don't actually know what connections are happening internally. You're not able to secure it because you don't know what they are. And that, as you saw in the diagram before, it's clearly complex. It's clearly something that's going to be difficult to determine accurately. But from a security and regulation perspective, the primary problem is there's a lot of services that can move money. We're a bank, there's a lot of different ways that money can be moved. And lots of services could talk to those services even though they're not supposed to. And that's a huge concern for us as a security team. It's also a huge primary concern for regulators. You want to be showing some isolation between things that handle employee management and things that handle money movements. So that was a big concern, and solving it was kind of the top priority at the time. And instead of just identifying a list of services that needed high security, that's a list that becomes stale. We kind of wanted to think, what's the security that we want to obtain? What's the strict controls that we want? And then can we make it generic and automatic and manageable enough that we could just apply to all services? Why only have a few high security services? Why not just treat all your services like they are really dangerous? And that actually means that we don't have to maintain really accurate lists of which services do scary stuff and which don't. And that's where vulnerabilities could really arise from if we got that wrong. So we wanted total peace of mind with a generic solution that applies to all services. So we started to think about how this might look like by doing a single really strict network policy. And that applied to our banking ledger, which is kind of the core description of all transactions that have fundamentally occurred across the whole business. So that's a really important service, and it's the kind of service that can literally invent money out of thin air if you can get it wrong. So we obviously wanted to restrict that as much as possible. And it actually worked fine. It's rolled out safely, and it worked fine for a long time, but we didn't have any illusions that we could scale this to another 1,000 services. First of all, one of the problems is that the owning team has to review every new client. So this is a network policy that literally has a list of every label of the services that are allowed to call it. And that list lives with the other manifest for the service, which means it's owned by the owning team, and they have to review everything. And they actually wanted to be able to review everything, so this was helpful. But most of the time, teams don't care about new callers of their services. They would be spending a lot of time reviewing that in some cases. So that's not very helpful in all cases. We want that to be optional. And the other problem is that this policy also has to allow things like Prometheus and upstreams that have to call everything. And that's not state we want to duplicate everywhere. And also, we were just maintaining this manually. We had some pretty basic static analysis to remind engineers to update it, but fundamentally, this was a pretty scary manual operation. We needed to move to a declarative model for rules, by which I mean the fact that a service calls the ledger is not really a property of the ledger, it's a property of the calling service. We want to identify that securely, and we want to be able to review it in some cases, but it still should live with the calling service in the monorepo. And if you maintain it as a property of the ledger, you lead to all kinds of edge cases. The primary one being rollbacks. So if you roll back the ledger to before one of the clients is allowed to access it, but you don't roll back the client, you have an incident. And that's very scary. And that did even happen. So it makes this very, very difficult to deal with. We also just want to shield our engineers from working with these kinds of policies. We want to give them very thin keyholes with which to interact with Kubernetes, not writing arbitrary network policy YAML files. And the information we need from an engineer is A equals B. We don't need them editing a manifest to assert something as simple as that. And lastly, we didn't really have a way to test policies like this. So when we rolled out this policy, we checked it manually, countless different ways, thinking about every different way that something could call the ledger. We checked it against metrics, and then we basically just roll it out to one pod and check for connection errors. Now, those errors would have been retried, so we knew that was essentially safe, but we can't do that for 1,000 more services, and they wouldn't always be safe in all instances. So the first step towards moving towards a generic solution is to take the basic static analysis that we had built and make it really generic and as accurate as possible. And we turn this into a tool called RPC Map. Sadly, it's kind of very specific to the way that our RPCs look like in our platform, but I'm sure that you could write the same thing for gRPC. RPC Map would scan all of the imported packages for a service and look for things that look like RPCs. It would have a list of exclusions for certain edge cases, and then it would turn them into files called rule files. And the reason that files are a really awesome way of describing these links between services instead of like a list of services in a YAML file or whatever else is, first of all, that you can use code owners. So a service like the ledger, you can essentially write a code owner on all the rules that allow something to call the ledger, and they would have the ability to then review new callers. But that's now optional. Second of all, you can use tools like find and grep to look through your whole code base and determine what's allowed, what connections are occurring. That's really useful. So I really like this approach of using files, just empty files. And down the line, we can even decide to add metadata to these files. So the files could actually have some kind of text format inside them that would do things like allow endpoints, specific endpoints to be used. So that is really powerful. I really like it. What does this actually mean in Kubernetes land? Well, we have a deployment pipeline at this company, which allows us to take the code in the monorepo and the manifest in the monorepo, package them up into a Docker image, and package them into the Kubernetes manifest, and then deploy them, right? So we decided that we wanted to compile these rule files into Kubernetes pod labels. So something like service.ledger.rule becomes bank.com/egress/ledger equals true. And having labels to determine all the dependencies of a service is super useful. First of all, you can just list all pods that call the ledger in Kubernetes, which is really useful and very fun to do. You can also read a pod's label and determine all of its dependencies, which is helpful. And you can use it programmatically. So for example, our envoy control plane, instead of giving you access or giving you configuration for all services and giving you a lot of expensive endpoint updates for that, instead, we just give you the ones that the labels say you're allowed to call. And that's a massive performance optimization. You reduce the amount of envoy endpoints that you're sending by like 1,000 times. And that massively improves latency. It's not security control necessarily, but it is very effective performance control. But where things get interesting is obviously now that we have these labels, we can use them in selectors in network policies. And these network policies are now so simple. They're almost identical for every single service. Instead of listing labels that are allowed to call a given service, you instead just select on all the pods that have a label saying, yep, I can call the ledger. And it makes the policy really simple. And the other trick that we used is every pod that gets one of these network policies, which obviously at first is none of them and eventually becomes all of them, we also give it a label just network policy true. And now we have a label for everything that already has a network policy. And that's super powerful because the first network policy for a pod is dangerous. It restricts its inbound traffic. But the second network policy for a pod can only increase its traffic. So it's always safe to write policies on things that already have policies. That's a guaranteed safe operation. And that means we can write global policies. So we can select on every pod that already has a network policy and do things like allow Prometheus. And that's always going to work. The other advantage is every policy is going to select on that label, which means that if you remove the label, you're going to drop your pod out of every policy. It's like removing all the policies in the entire platform, but just for that pod. And deleting network policy in general is very dangerous, but deleting this label is always safe. This is really useful for debugging. Obviously, some services do unusual things. They have weird inbounds, they have weird ports, they have node ports maybe. And in those cases, we actually had customized patches. So the policy that you're seeing here would almost never actually be written down. There'd be a base manifest and it would apply to all other services. But some services would have patches on top of that, allowing extra ports or allowing extra labels or whatever else. And what's so cool about that is that you now have a programmatically describable list of all the services that are weird. And anyone who, like me, has had to manage a lot of microservices can attest to the fact that it's not really about the 1,000 services that all look the same. It's about the 300 services that do weird stuff. In this project, I spent 95% of my time worrying about the weird services. So having those written down in a programmatic format is so powerful, and I would really recommend that to anyone. So we were now ready to write these for every service, and the question was, how do we roll that out safely? So the model works. The source of information, the rule files, is relatively reliable. But not all inbound connections look like RPCs. Not all of them are even in the code base. And even within the code base, there are going to be exceptions that RPC map can't determine. Things like if I build the service name programmatically in some way, something weird like that. Using metrics from Envoy get us some of the way there, but not everything goes through Envoy. Our staging environment gets some of the way there, but not everything's going to get caught in staging. It's not acceptable to just hope that the instance that these problems cause won't be that bad. You have to plan for them, and you have to explicitly say, no, we're going to catch all issues. We're going to prove this to ourselves. What we wanted was a warn mode. And it would be awesome if network policies had this kind of feature by default, but you can kind of hack it together. And by warn mode, I mean, you want to know what a policy would drop or what packets would be getting dropped with your current set of policies, but without it actually being dropped. And this is actually really easy to do with Calico. You essentially want a policy that runs last after all other policies, and therefore packets will only reach it if they are not already accepted and they're going to be dropped. And then in that policy, you want to log, which means it'll essentially go to the kernel log, a full description of the packet that's been dropped, and you then want to allow the traffic. So what that means is all packets will never be dropped, but they'll always be logged if they were going to be dropped. So we call that a dry run policy, and in Calico, that's very easy to write. And we run this tool called kube IP tables tailor. It runs on every node, it tails the kernel logs, and it turns these log lines into Kubernetes events, and it turns them also into metrics. And that makes it really easy to track what packets weren't being allowed. You can basically get the Slack message for every single packet that gets dropped, which is really awesome. But where this goes wrong, and where this did go wrong, is if you log a lot of packets because you rolled out a really bad policy, maybe accidentally, and I did do this, the kernel will be logging so much that you can essentially take down networking on that host. That is not a lot of fun, and it's not very easy to debug. We spent a long time thinking this must be AWS's fault, and no, it was not. It was kind of my fault in some sense. So we started to think, is logging overkill? Like, we don't need a log line for every packet. We kind of just need to know that packets are being dropped. As long as you know that a service is receiving traffic that we haven't specified, you can usually figure out what the reason is. You can go and look at the service. What's weird about the service? Where might it be receiving traffic from that's unusual, that RPC map wouldn't notice? And you could almost always figure it out. We don't really need to know this amount of information. It's very helpful to get things like source IP and the ports and stuff like that from the packet information, but most of the time it's just, we need it only if you can't figure out what's going on, and that's rare. So we wanted to know how many packets are hitting this policy, being accepted by this policy, and for what pods. Fortunately, this is possible with Calico as well, because Calico policies are just IP tables rules, right? And IP tables rules have counters, and those counters can be scraped using a Prometheus exporter, and we wrote one of these. It's called Calico Accountant. It's going to essentially, every time you scrape it, it'll do IP table save, it'll pass out the packet counts, and it'll determine which chains, and those correspond to pods, and which policies, how many packets have they accepted, and then if you plot those as rates, it's very straightforward. So you have to actually use the Calico API a little bit to sort of turn these names that you see on the slide back into pod names and back into policy names, but that's pretty easy to do. And then after that, you essentially have the rates for every policy, for every pod in your entire platform, and you also have the rates of packets that are actually being dropped that haven't been accepted by any policy. And that is a very useful metrics to have. And I would basically recommend that anyone running Calico considers running this tool, because it's incredibly powerful and it's incredibly easy to set up. Once we had that tool, in conjunction with the logging, for instances where we couldn't quite figure out what was going on, we basically fully specified the whole system. It took about a month, and by the end of the month, we were seeing 0 drop packets every day. Every single one was going into a Slack channel, and there basically just weren't very many. And we investigated every single one. So at that point, you can turn on enforcement. And the way you do that is you just take your dry run policy, which is currently logging and allowing, and instead you just log. So we're still getting the Slack messages when packets are going to be dropped, but you don't actually allow them anymore, so they do actually get dropped. And this was boring by the time we did it. I mean, it was meant to be boring, right? It's such a straightforward change, and it doesn't really change anything because it was affecting, we knew that it was affecting no packets, but it's probably one of the biggest step changes in the security of the platform that's ever happened. Because suddenly you're now in a scenario where an attacker that's somehow in a pod on our network, except for a few other pods that it's supposed to be allowed to call, if they do any kind of basic internal exploration, send out some curls or whatever else, we are going to get a Slack message for every packet that they send, which is a difficult position for them to be in, I suspect. So that was really awesome. So it's about a year later now. I don't work there anymore, but I have it on good authority that things are running pretty smoothly. Engineers maintain their rule files using RPC map. RPC map usually means they don't have to think about it very much, and it gets reviewed in the pull request. And quite a few teams actually ended up taking advantage of the fact that you can set code owners on all the rules for a service and then review all new callers. A lot of payments teams started to do that as a standard practice when they're writing a new sort of dangerous service. And that's really awesome. I'm glad we supported that. We don't really see very many issues related to bad rules. RPC map catches most things. Staging catches a lot of things, and metrics as well. And the system is incredibly tightly specified. We've got 13,000 rules or rule files in the monorepo. We've got 1,500 services, so that's 8 services on average that you can reach out to. And previously that number was 1,500. So that's a pretty incredible change. So what's next? Well, having spent a few months thinking about internal network traffic and network isolation, the obvious extension to that is what about traffic leaving the platform? And obviously, the first thing that an attacker will do a lot of the time is pull down a payload from elsewhere, maybe GitHub or wherever else, some hosting provider. So we essentially want as many pods as possible to have no public internet access whatsoever. We want to give them S3 and maybe internal S3 buckets. Maybe we want to give them some Amazon APIs, but we probably don't want to give them the whole internet. We want to restrict that as much as possible. And then the services that can have public internet access, we don't just want to give them the whole internet, we want to give them the websites they actually need, or in particular the DNS names that they actually need. And there's a few CNIs that can provide this functionality, and you can also do it with Istio, but we actually wanted something that tightly integrated with our existing network policy setup. So we wanted to use the same rule files, essentially, and the same pod labels, and then have the effect of, instead of restricting to services, we restrict to external services. And we created an operator for this. It's called egress operator. You can look it up, tiny.cc/egress operator. And I hope to talk about this at another KubeCon someday, but you might be interested in looking into it. It's really awesome. And I'm sure that some people looking at this talk or hearing this talk will be thinking and will want to ask me about, why didn't we use Istio? Why didn't we use mutual TLS, certificates, declarative, etc.? Calico network isolation is really the first step of a longer-term strategy, which will involve isolation on a per endpoint basis. We definitely want to be able to say things like, you can use the read endpoint, but not the write endpoint for this service and stuff like that. And there's loads of instances where the security of network isolation is really compromised by the fact that a service has dangerous endpoints and safe endpoints. This hasn't been decided yet, but we're thinking pretty closely about using Istio. It's very easy to translate our existing network policy model into sort of Istio language. And obviously, we already have an envoy sidecar service mesh. So it wouldn't be a very difficult migration to move to another envoy sidecar service mesh, which obviously has a lot more features on the service mesh. And it's also very helpful for us to have mutual TLS, for us to have encryption. And we don't just want to rely on network segmentation, but it is true that network segmentation is very meaningful to auditors and regulators, and it is therefore valuable for us to have that control as a base. And then it's additionally would be even more valuable to also have encryption and certificates and genuine authentication. So that's something that hopefully we can do in the future. And that's everything that we have time for. Thanks so much for listening. This whole talk is basically adapted from our blog post, and you can read about that at tiny.cc/network-isolation. You can also follow me on Twitter, Jack Kleeman, and you can email me about this, or my future self in the Q&A, I'm sure can answer any of your questions. And thanks very much. That's all. Hi, everyone. Thanks for coming. I hope everyone can hear me okay, etc. I think most of the questions I've already answered, but there's one left, and there's probably some more that will come in while I answer. So one from Kevin saying, what are my thoughts on using network policies for traffic flow in and out of the cluster? So I touched on this a little bit with the egress operator that we worked on. I think we started to realize that most attacks would involve some kind of egress or some kind of traffic leaving the platform to reach an attacker's platform, or obviously, yeah, if you're running like hybrid cloud or on-prem, it might be reaching other things. So I think, my basic stance on this is that all traffic should be specified. I mean, in practice, you should have network policies for everything, and you could start off with very generic ones that allow a lot of things and try and scope them down over time. And that should include, things getting out of Kubernetes and basically try and have as much restriction as possible. Even if it's not necessarily a security priority, I think it is so valuable, and I touched on this a little bit, to have a programmatically queryable list of things that are happening in your cluster that's provably true. Like, that this set of policies is a superset of the traffic that's actually happening. I think that's amazing. And just for the kind of monitoring and kind of headspace benefit of that, I would advise it, even if security isn't the top priority. But yeah, I would definitely be keen on using network policies for as much as possible. Another question from Gaston. When using Istio, the network policies for kube system and other namespaces aren't protected. Yeah, I think we would never have planned to exclusively move everything over to Istio and just dump all this work that we've done. I think we would see it as, and I think Istio to some extent recommends like some usage of network policies in some areas. Defense in depth is the name of the game, and it's never acceptable to have just one control. And actually, when you're dealing with regulators in particular, it's never acceptable to just have one control. So we would have layered Istio on top of this to add endpoint level security and encryption and more authentication power. But we wouldn't have removed what we already have. I think network policies, like, they're my favorite resource in the whole of Kubernetes. They're so powerful. I'm excited for V2, but I think that they have a lot of power already. And I would really advise that. Next question from Rolf. Have I thought about an ingress operator? I don't really know what that would look like, because it's already possible to have a lot of control over ingress. You can essentially not allow pods to receive traffic on host network you can only allow it to happen through like certain network ingresses to your CNI, and then you can have API gateways for those things. So that's probably what I would recommend. I don't know if it's quite the same solution. The same thing just does not apply for egress. Generally, all pods have total access to like the internet, and that was the thing that we were concerned about. But certainly at this company, it was not possible to reach a pod from an external place. You would have to go through some kind of software-defined network ingress, and that had all the power that we needed. Question from, I don't know if I'm saying this right, Nsx. How did you create the diagram in the beginning? Really simple, actually. So it's take the rule files, you run find to get a list of them, you use sed to turn the list of file names into dot file syntax. So you take the first part, which is the name of the calling service, and the last part, which is the name of the recipient service, and you put an arrow in between them, and that's now dot syntax. Now you have a dot file, and you use a piece of software called Gephi, which turns dot files into beautiful graphs. And then you do some sort of graph positioning algorithm that sort of doesn't work very well, but it'll work okay. And that's how you do it. It was super easy. So this is the awesome thing about having these files. Next up, how I thought about Nsx Micro Segmentations. I don't know what that is, so clearly I haven't thought about it, but I would love to hear more if you can elaborate on that. And finally, is there a possibility to use kube IP tables Taylor without switching from Cake network policies to Calico network policies? So first of all, you don't need to switch to Calico network policies. You just need to have a single policy that logs everything and then allows everything that runs late. And it's not currently possible to log using just Kubernetes policies. If you're already on Calico, it wouldn't be very difficult to create a PR against Calico or to fork it specifically against their Calico kube controllers, which is a pretty simple controller that would allow you to label a policy such that A, it runs last, and B, it logs. That seems possible to do because you can definitely write a policy that allows everything. The things you're missing are ordering and logging. You can trick the ordering thing with alphabetical naming. I'd recommend that. But yeah, it probably is possible with other CNIs as well. Cool. Apparently my sound's gone. Is my sound back? Yeah, sounds like it is. Okay, great. I was just saying about, you do need a few features of Calico. Other CNIs might need it. You need it to run last. You need it to be able to log, and you need it to affect all namespaces. Or you can create a policy per namespace if you need to, or you can write a controller that does that for you. But running last is often possible if you name the policy in a certain way. And logging, that's the tricky one. And we, at one point, even forked Calico to have this functionality, but we decided in the end to use Calico global network policies. From Bart, is RPC map required to set up the dot rules? Yes, it is. That was a very much a homegrown thing. It was parsing our code to look for things that look like our RPCs. They're not gRPC. And they create rule files for you. You would have to build something similar. And if someone builds that for gRPC, then that would be incredible. But I don't know what that would look like. It's not required for Calico Accountant. Calico Accountant is an incredibly generic tool. It just looks at your Calico rules, turns them back into policy names, and tells you what's going on. It's really awesome, and it will work for everyone using Calico. So I really advise that. And I think that's everything, unless there are any other questions. That was really fun. Thank you, everyone.